All right, so in this video, we're going to look at an example where we verify the divergence theorem. If you recall, the divergence theorem states, so we're going to look at an example where we verify that this holds true. So for our example, we're going to say that our vector field is equal to, and we're going to say that our region is bounded by 4 planes. From this vector field and this region bounded by 4 planes, we are going to verify that the divergence theorem holds true. So to solve this problem, I'm going to start by first sketching what this region looks like. So really, these 3 planes are pretty self-explanatory. It's this one that's the most complicated. Well, we could sketch this plane by determining the x, y, and z intercepts. So for the x-intercept, if we set y and z equal to 0, we get 2x equals 2, which means x equals 1. For the y-intercept, you could set x and z equal to 0, you get y equals 2. And for the z-intercept, you set x and y equal to 0, you get 2z equals 2, which means z equals 1. So really now we just plot these 3 points. And so if I connect all of the intercepts together, I form a triangle. And this triangle that I've drawn here represents this plane. But notice that there's 3 other triangles. This one, and this one. Well, those other 3 triangles are represented by these 3 planes. So in reality, we have a total of 4 triangles here. So the region bounded by these 4 triangles represents this region. And that's really the whole idea. So now we know what our region looks like. So now, using this vector field and this region, we are going to verify that the divergence theorem holds. In other words, we need to verify that the left-hand integral is equal to the right-hand integral. So we'll start by evaluating the left-hand integral. For the left-hand integral, we need the divergence of our vector field. If you recall, the formula for divergence is, and so really, the x and y components of our vector field are both 0. So really, these 2 terms go away. And for the z component of our vector field, well, the z component is z squared. The derivative of z squared with respect to z is 2z. So this will be the integrand. Of course, a volume element would be dx, dy, dz. So now, since we have 3 differentials, that means we're really evaluating a triple integral. So I'm going to rewrite this integral, but it's going to be a triple integral. And so notice how I've rewritten this in a different order, right? That's perfectly fine. What this means is I'm going to integrate with respect to z first, then I'm going to integrate with respect to y, then I'm going to integrate with respect to x. So really, I need to think about my bounds of integration. So we'll start with z. What are my bounds of integration going to be for z? Well, let's look at our region and think about the different z values that we could have. Well, the lowest z value occurs when z equals 0, right? Z equals 0 is the lowest z value for this 3D region. So this red region that I've drawn here is the lowest z value for our entire region R. So we'll start at z equals 0, but then we're going up to, well, if you choose any point in the red region, and you go as high up as you can until you exit the region, you would end up somewhere on this plane. So really, I'm going to solve for z in this equation. You would get this. And so really, I'm going from z equals 0 to z equals this thing. So these would be my bounds of integration for z. Now I need to think about my bounds of integration for y. Now to determine my bounds of integration for y, I need to think about where I started with when integrating with respect to z. I started in this red region. So we're going to think about the different y values in this red region. Well, if you think about the lowest y value in the red region, it's going to be y equals 0. It's going to be basically this line right here, y equals 0. But then to determine your final endpoint, you choose any point on this line where y equals 0, right? And you go as far as you can in the y direction until you can't go any further, which will basically be any point on this line. And so really, to determine what this line is, we have to determine the equation of this line, right? But basically, all this line is this equation, except you set z equal to 0 and you solve for y. So if I take this equation and I set z equal to 0 and solve for y, you get this. So this is the equation of this line. So really we're going from y equals 0 to y equals negative 2x plus 2. So now, lastly, we have to determine what we integrate with respect to x, right? What are our bounds of integration with respect to x? Well, we have to think about where we started with when integrating with respect to y. Well, we started on this line right here, right? Which really goes from x equals 0 to x equals 1. So we're going from 0 to 1. So determining these bounds of integration is something that you should be able to do, right? So now it's just a matter of evaluating this integral. And so let's do that, right? Let's spend the next 20 minutes of our lives evaluating this integral, right? That was good, right? That was a good one. So let's do that. Well, I'm going to first start out by evaluating this integral, and I'm going to call this integral number 1. Well, the integral of 2z with respect to z is z squared. And our bounds of integration go from 0 to this thing. So now I'm going to perform the substitutions, right? It's going to be this squared minus 0 squared, which is really just this squared. So this is the answer to integral number 1. So now I'm just going to resubstitute this back into this entire thing. So now we're going to determine the second integral, and I'm going to call this integral integral number 2. So that is the integral we are going to be evaluating next. Right? But I'm going to have to erase this, but we need to remember that these two things are here. So I'm just going to move these two things back up to the top for safekeeping. So we can come back to that later. So now we're actually able to integrate all of these terms with respect to y, right? It's just the reverse power rule, right? We treat x as a constant and y as the only variable. If you integrate all of these terms with respect to y, you would get so now it's a matter of performing our substitutions. So it's going to be the substitution of y for this minus the substitution of y for 0. But in reality, if you subtract the substitution for 0, you're overall just going to be subtracting 0. So all we have to do now is just substitute all of the y's for this. So now at this point, you can see a bunch of things cancel out. In fact, everything right here cancels out, and this is all we're left with. I'm just going to rewrite this back at the top right here. And so just to make this look a little nicer, I could factor out an 8. And so this is what you would get. So now I'm going to go back to my original integral, which is this one, which is. So now I've taken this and I've put it back into here. So this is back to our original integral. Now really I could pull this constant out. 1/4 times 8/3 is 2/3. So now we just have to evaluate this integral, which I will do right now. And so the answer to this integral is 1/6. So now we have evaluated the left-hand integral to equal 1/6. So now we want to verify that the right-hand integral also equals 1/6. So that's really the whole idea. So now we're evaluating a surface integral. Now really, the surface of our region can be broken up into 4 individual surfaces, right? And each of those 4 surfaces are described by these 4 planes. So really, we're going to break up this surface integral into 4 individual surface integrals. So I'm taking the surface integral of this entire region, and I'm breaking it up into a sum of 4 individual surface integrals. Okay, so really, each of these planes have their own normal vector, right? That's why I've labeled them differently. So let's think about the normal vectors first. As for the normal vectors for each of these, for x equals 0, right, we have to think about where that is to get a visual understanding of what the normal vector would look like. So what I'm actually going to do is I'm actually just going to redraw this. So again, 4 planes, 4 triangles that make up the figure. Well, for the plane x equals 0, that would be this face right here, right? This face would describe x equals 0, right? So really, the outward unit normal vector would point in the negative x direction. In fact, it would be negative I. Likewise, for y equals 0, that would be this face right here. It would point to the left. It would equal negative j. For surface number 3, that would be z equals 0, right? And that points in the negative k direction. So these ones are pretty easy. But for surface number 4, it's a little bit more complicated. In fact, I'm going to evaluate the unit normal vector for surface number 4 individually. Now, a normal vector for surface number 4 can be determined just by looking at the coefficients in front of x, y, and z. In this case, 2, 1, and 2. You get 2i plus 1j plus 2k. This would be a normal vector to this plane. Notice it does point outward away from the region, right? This points in the positive I, positive j, positive k direction. It's pointing away from the whiteboard in this direction. That's the direction that this normal vector is pointing towards. So we know it has the correct orientation. We just have to convert this into a unit vector. So really, to convert it to a unit vector, if you were to calculate the magnitude of this vector, this would be equal to 3. So really, if we were to divide this entire thing by 3, you would get 2/3 I plus 1/3 j plus 2/3 k. So that is what N4 would be. So now, let's think about how we can rewrite these surface integrals. Well, notice that the integrand for each of them is the vector field dotted with their corresponding normal vector. So really, for our first surface integral, we're doing z squared k dotted with negative I. But remember, k dot I is equal to 0 because, if you recall, I, j, and k are perpendicular to each other. So if you do this vector dotted with this vector, it's going to be 0. So you'd be doing the integral of 0, which we know is 0. So really, this first integral is just 0. It goes away. For the second integral, well, really, you're doing z squared k dotted with negative j. But again, k and j are perpendicular to each other. So really, v dot n2 is 0. The integral of 0 is 0. Now we do v dot n3. Well, z squared k dotted with negative k, well, that's not 0, right? Z squared k dotted with negative k is actually negative z squared, right? But, I like that, that was good, right? But z is equal to 0 for surface number 3, right? Surface 3 corresponds to z equals 0. So really, this is the integral of 0, which is 0. Haha, looks like we got another 0. Let's go, right? We don't even have to do that one either. But clearly, since this surface integral needs to equal 1/6, this integral better be 1/6, right? Well, it turns out if you do v dotted with n4, you're really going to be doing z squared k dotted with 2/3 k, right? Hopefully we can all agree with that. Well, z squared k dotted with 2/3 k is 2/3 z squared. So really, this integral better be equal to 1/6. One question you might have is, what is d sigma 4? Well, d sigma 4 is a surface element of surface number 4. In other words, it's a surface element of this plane. That's all it is. Now, here's the thing. To determine what this is, there's something you need to remember. For anything that's in the form of z equals f of x comma y, you can calculate the surface element for this thing. It turns out it's equal to this. Right? And in this particular case, d sigma 4 comes from this plane. Right? And we can re-express this equation in the form of z equals f of x comma y. In fact, we did this before. We got this. And then we could rewrite this as, right? Because this is going to help us calculate the partial derivatives. So really, the partial derivative of z with respect to x. Well, the partial derivative of z with respect to x is -1. And the partial derivative of z with respect to y is -1/2. So then if you were to simplify this, you would get, which simplifies to, so this is what d sigma 4 is. That's how you would calculate that. So now I'm going to replace d sigma 4 with 3/2 dx dy. So this is it. But here's the thing. We're no longer integrating over surface 4. We're actually integrating over this triangular region right here. Right? It's basically the projection of this plane onto the xy plane. Right? That's why we have dx dy. So really, we're integrating over this blue colored region that I'm coloring in right here. That's the region we're integrating over now. So I'm just going to call this region E. And so now let's determine what this integral is. Well, first off, notice that the 3 and 2 cancel out like that. We are going to convert this into a double integral. Right? So we're focusing on this blue region. I should probably state that this was a 1, this was a 2. So, bounds of integration for y. So really, if we think about the lowest y value in this region, it's y equals 0, right? This is our lowest y value, y equals 0. But really, if we take any point in the blue region where y equals 0, right, and we keep going in the y direction until we can't go any further, we will reach this line. But remember, we already determined the equation of this line, right? If you recall, it's y equals -2x plus 2, right? We did that way earlier on in the problem, right? When we were evaluating this integral, right? The equation of this line is y equals -2x plus 2. So really, we're going from 0 to -2x plus 2. And then we integrate with respect to x. Well, we need to think about where we started with when integrating with respect to y, which means, well, we started on this line right here, right? So really that goes from x equals 0 to x equals 1. So remember, for this integral, z is equal to this. Because remember, this integral came from the surface integral over surface 4. So really we know that z is equal to this. So I'm going to go back up here and I'm going to substitute z for this. So now what I'm going to do is I'm just going to algebraically expand this thing out. And so this is really what we get. I'm going to resubstitute this back into the integral. So resubstituting this back into here, I can put the 1/4 to the outside. And so now at this point, what you should be able to recognize is that this is the same exact integral that we were evaluating before. This is the same exact integral that we evaluated when calculating the left-hand integral. So we know, since this is identical to what we were doing before, that this will result in 1/6, right? It's the same exact thing, right? Remember, all that stuff's going to cancel out, you're going to be left with 1/6 if you were to evaluate this thing. And so this is basically how it would work. And so now we know for a fact that this right-hand integral will also equal 1/6. And so, as you can see, this would verify the divergence theorem for this particular example. And so this is basically it for this video. As you can see, it's a little tedious because it's kind of like a really annoying integral, but it's so good, right? Doing that's so good, right? This was a fun one, right? So hopefully you like this. This was good, right? So this is basically it for this video.